Well, welcome back. This is Unit 3.1, and this is on electron configuration, which is going to be in Chapter 5. And atomic structure, like how an atom is built, protons, neutrons, and electrons, that's in Chapter 4. But that is not something we're going to spend a lot of time on because that should just be a review for you from junior high and grade school. All right, so just a quick review though. The atom is made up of three parts. These are called subatomic particles, and this is the proton and the neutrons that are in the nucleus, and the electrons on the outside of the atom that are traveling around the nucleus. So you have your protons and neutrons in the nucleus and the electrons outside. Protons are positively charged. Neutrons are neutral, they have no charge, and electrons are negatively charged. Okay, and there's 5 scientists that we need to know, and we need to know their contributions for chemistry, and that is Dalton, and his contribution is the atomic theory. J.J. Thompson, who discovered the electron. Rutherford, who discovered the nucleus. Bohr, who discovered or made the planetary model of the atom. And Schrdinger, who came up with the quantum mechanical model for the atom. Okay, so first of all, we have Dalton's atomic theory. And Dalton's atomic theory said 4 things. And Dalton came up with this way back in the early 1800s. So that was the first statement of his atomic theory says atoms are small, very, very small, and they can't be broken down into smaller parts. So if you keep dividing and dividing and dividing matter, the lowest or the most smallest part that you're going to get is called the atom. It can't be broken down any more than that. And atoms cannot be created or destroyed. His second statement said that atoms of one element are the same, like all carbon atoms are going to be exactly the same, but different atoms are made up of different amounts of particles. So all carbon atoms are the same, but they're different, say, than nitrogen atoms. The third statement is that atoms combine in set ratios to form compounds and molecules. And the fourth statement is chemical reactions break down and rearrange atoms to form different compounds. This was a big deal back in the 1800s coming up with this. It was very leading edge. All right, so J.J. Thompson, we said, discovered the electron. He did that by an experiment where he used a cathode ray tube, which is just like a radio tube, and he emitted a beam of light that went straight forward. And right here on the top of this tube, he put in a negative electrode, a negative plate, and here on this side, a positive plate. So the beam of light would go between these 2 plates. And when he electrically charged this with a negative charge, he saw that the beam of light would deflect downwards. Okay, and then he put in a positive charge, and he saw that again, it deflected downwards. So using information that he knew that charges that are the same repel each other and charges that are different attract, he deduced that these particles in this beam must be electrons. They must be negatively charged particles, which he called electrons. So he came up with this model called the plum pudding model. J.J. Thompson was British, and so very popular dessert back in his time was plum pudding. And he said that the pudding part, so you're looking down bird's eye view on a bowl. And so you have this pudding part here that he said was the positively charged part of an atom. And then plum pudding had these little bits of cut up plums that were in the pudding, kind of like, I don't know, raisins maybe that we would have in pudding today. I mean, these little bits of plums were the negative parts of the atom, and they were just floating around in the pudding. Okay, and so plum pudding model for J.J. Thompson, his cathode ray tube experiment. J.J. Thompson and Rutherford were colleagues. They worked in the same lab, and Rutherford discovered the nucleus. And the way he did that is he had this a radioactive particle source that emitted alpha particles. And around that, he surrounded like X-ray paper or X-ray sensitive material. And between the paper or the material and the particle source, the radioactive particle source, he placed a very thin sheet of gold foil. And if you don't know what gold foil is, it's very, very, very thin gold. It's just a few molecules in width. And so he shot these particles through this gold foil. And what he saw was that most of the time, the particles would go straight through and would leave these white flashes of light on the opposite side. But occasionally back here on the perimeter, he would see little flashes of light back here. So what he deduced is that most of these particles, like if this was the gold foil here, just a couple of atoms thick, most of the particles, the alpha particles he shot through, would go straight through. They wouldn't be obstructed by anything. But occasionally they would strike something like this one here and deflect, okay? Or they would actually hit straight on and ricochet back. And so what he deduced was that the atoms had a very, very dense center, okay, that these were hitting and bouncing off of, and he called that the nucleus of the atom. Okay, so Rutherford discovered the nucleus. Bohr, Niels Bohr, he was a colleague, contemporary that lived about the same time, but he did not work with Rutherford and Thompson. He was Danish. And so he came up with what's called the planetary model of the atom that said that you have your nucleus here, and then at regions around the nucleus, you're going to find where the electrons are orbiting around, kind of like the planets orbit the sun, and that there's going to be some empty space, and then you would have another orbital where electrons were, and then you'd have another region of empty space, and then another region where electrons would orbit around the nucleus. And we still use Bohr models today to help us explain the electrons' arrangement around the nucleus. And we'll be talking about Bohr models. And the Bohr models are probably what you made in junior high or grade school, elementary school. If your teacher said, okay, now you're going to make a model of this atom. And so what you would do is you'd put a styrofoam ball in the center, and then with coat hangers or whatever, or sticks, then you would put electrons like another smaller styrofoam ball on a stick, and that they would be around the nucleus. So what you were doing was making a Bohr model. And then last, Schrodinger, this is like in the 1920s, he came up with this, and it's what we call the quantum mechanical theory. And what he said was that electrons don't follow paths like this around the nucleus. They're randomly moving around in random patterns in regions around the nucleus. And so he dubbed, electron cloud is the term that we get from Schrodinger's model. And there's different shapes of orbitals that these electrons exist in. For example, this one is called the s orbital, and it's spherical. And what you'll see here is this black dot is like the nucleus, and then these aren't individual electrons. This is kind of like a moment in time. The electron may be here, and then in a moment in time, it may be here, and then in some moment in time, it may be here. So you take all of this collectively together, and it makes this hazy spherical shape around the nucleus. And another path that these may follow is called a p orbital, where it looks like a bow tie, but then you have this in the x, y, and z axis. And when you overlay those, it kind of looks like this. And then we come up with electrons that are in a d orbital. So it has this clover shaped, and that's in the x, y, and z axis. But there's also one on this plane. And then you have one that kind of looks like a donut with a bow tie. So it gets very, very complicated. And so we diagram electrons around the nucleus using Schrodinger's model. And that's what we're going to talk about when we start talking about electron configuration. But before we get into that, I'm going to do a little activity. So we have 3 rules here, and these are actual rules before I get into the activity, that electrons are around the nucleus, how they're placed around the nucleus. So the first one is called the Aufbau rule, and the Aufbau is a German word that means to construct or to build. And so the Aufbau rule says that electrons fill the lower energy levels first, and we'll talk about energy levels in just a second. Then we have the Pauli exclusion principle, which is the maximum number of electrons that can fill an energy level is 2. And then Hund's rule that says orbitals that do have 2 electrons in an energy level must spin in opposite directions. So please pause the video and write these down. All right, so the activity that we're going to do to illustrate this is called Hog-Hilton. And the premise of this is that we have this hotel that's built like an inverted pyramid. So it's very small at the bottom, and then as you go up in the floors of the hotel, it spreads out and gets much bigger. So on the bottom floor, since it's the tip of the pyramid, inverted pyramid, there's really only one room. And as you go higher to the second floor, there's only 2 rooms. You have this room that's on one side of the hotel, and then this room that's on the other. So there's a hallway that you have to walk down to get to these rooms. And the same thing on the 3rd floor. Now, when you get up here to this level, then you have, the room here, and then a long, long hallway. And on the other side of the pyramid, you have this one, and then a long hallway. And then on the 3rd side of the pyramid, you have this. And I guess in the 4th side of the pyramid, they use it for storage or something. So these are the rooms that are on these hallways. So the premise is we have all these hogs coming in for a convention, and you run the Hog-Hilton, and you're going to have to make sure that you keep these hogs or keep a ledger of where these hogs are in these rooms so that you can put, them in the appropriate rooms. And the rules are that pigs are very, very lazy. They don't like to walk upstairs. This hotel does not have an elevator, only stairs. So they will not walk upstairs in order to stay in a room. The second thing about these pigs is that if they can stay in a room by themselves, that's what they would prefer. So they would prefer just to be in a room by themselves. And then the third thing about these pigs is if you do have to put them in a room with another pig, they don't like each other to the extent that they're going to have to face in opposite directions the whole time that they're in this room. Okay? And before they will walk up the stairs, though, they will room with a second pig. But when there's 2 pigs in a room, then they definitely will go back upstairs. All right, so the convention is happening 5 days from now. So 5 days before the convention starts, pigs start showing up, and you have to put these pigs in these rooms. So 5 days before, we have 2 pigs that show up. So we're going to put this pig here in this room, and then the second pig, remember, they don't want to go upstairs. They're very, very lazy. But they will be 2 to a room if they have to, but they're going to have to face in opposite directions. So the second pig, we're going to have to put in the room like here, but faced in the other direction. Okay, so the 4th day before the convention, 2 more pigs show up. So I guess they're showing up to the convention a little early so they can do some sightseeing or whatever. So 2 more pigs show up. Well, this room's already taken, so you're going to have to assign to the 2nd floor. So this pig is going to go up here. And then the second pig, it doesn't want to walk. They're lazy, remember, so it doesn't want to walk down this long hallway to get to these rooms. So this pig is going to room with this pig, but it has to face in an opposite direction. So there you go. You have that pig there. Okay, now 3 days before the convention, 4 more pigs show up. All right, so what we're going to have to do is we're going to have to put a pig here. That's 1. And then a pig here, that's 2. And then this pig here, we're going to pull 1, 3. So they, remember, 1 to a room until they get these 3 filled, and then they'll share a room. So now we can put this pig here. That's going to share with this pig, but it's going to have to face in opposite direction. Okay, so now we have those pigs arranged. So now we have 2 days before the convention, and 6 more pigs show up. So here we have room here in this in this room. So we're going to put this pig here in this room, and that's 1. Okay, 2. All right, so we have 4 more pigs to put in. So now they're going to have to go up the stairs. 3. Okay, and then before he'll walk down this long, long hallway, this pig would rather share this room but face in the opposite direction. So that's 4. Yeah, this is 6 pigs. Okay, so that's 1, 2, 3, 4. Okay, so 5 and now 6. Okay. All right. So now the last day before the convention, we have 18 pigs show up. So you're going to have to place 18 pigs now. So you're going to assign this pig to this room because it's empty. But now that this is full, they're going to share these rooms before they go up to the 4th floor. So that was 2, 3, 4, 5. Okay, so now it's filled up. So we're going to have to go up 6. And before we walk down this long hallway, this pig's going to share. So that's 7. Okay, now 8, 9, because they're going to share this room. Not share the room. 10, 11, 12. Okay, so now before it walks down this long, long hallway, they're going to share these rooms. 13, 14, 15, 16, 17. Okay, and then the last pig's going to have to walk down here by itself in this wing to be 18. Okay, so this is just a little example how you would put electrons in these diagrams, in these orbitals. And we're going to see this in just a second for real when we do real diagramming. Okay, so let's look at the periodic table. And the periodic table is divided up into these groups of sections. So here we see this pink section. Okay, this is called the s orbital. Let me get my pen here. So these 2 rows of the periodic table are signified as an s orbital. And then over here, we have this group, this square right here in green, and this is called the p orbitals. Okay, and then we have here in the center of the periodic table in this green, light green color, these are called the d orbitals. Okay, and then down here at the bottom of the periodic table, this 2 rows down here, this group is called the f orbitals. Okay, and so the lowest energy orbitals are going to be the s orbitals, and then the next highest is p, and then d, and then f. So the order of these are s, p, d, and f. And so when you're talking about orbitals on the periodic table, they get letters that are go in the order of S, P, D, and F. And you can see here S, P, D, and F. All right. And so I've written out some orbitals here. Now, the way we do, let's go back. The way we fill these is we start just like you read a book. So if you're right here, the first energy level, you read a book from top to bottom, left to right. Right? So we're going to start in the upper left of this periodic table. So right here is the energy level 1, and that's where we have this 1 designation. And then this is the S, so this is 1s. Now if we travel over, we don't see anything else on the 1 line. So we're going to go down to the 2 line now. So this is 2, the second line. The first orbital we see here is S. So this is 2s. So you see 1s, then 2s. Okay. Now if we travel over, this is just empty space here. Okay. The next one we get to is on the second energy level, but it's a p orbital. So it's 2p. Okay. So if we go back and look, we see the 2p here. Now we're going to get to the end of this line. There's nothing else there. So we're going to go down to 3. So here we have 3, The first energy level we're going to go through is S, so it's 3s, empty space, empty space, empty space. And then here we get to 3p. Okay, so if we go back, we see 3s and then 3p. And then we're going to run out of periodic table. Oops, I went the wrong way. Run out of periodic table, so we're going to go down to the next line, and this is fourth energy level. And we have the s orbital here. Now, we're going to hit, for the first time, we're going to hit the d. Well, the thing about the d orbital is that since this is on the fourth energy level, these electrons are even lower energy than the fourth level. So we signify that by putting them on the third level, but they're not in this row here. They're this row. So this is 3D, 3D. So if we look back up here, we see it as 4s, and then it goes down to 3D, and then it'll go back up to 4s. So these right here in this d orbital, their energy is one less than the actual row that they're on. Okay, so again, it's 4s, then 3d, and then it goes back up to 4p here. And we're going to see why when we start talking about bonding. Okay, then we're going to go 5s, and then it's going to drop down one less, so 4d, and then back up to 5p. Then we're going to start over 6s. Okay, and then here, see this? It gets into these. But we're not going to talk about the f orbitals at all. We're not going to do any configuration there. So the next one here would be 4f, but we're not going to do those. So we're going to just stop with barium right here. So the highest you'll go is 6s. Okay, now let's look back at that. So we have 1s, 2s, and then 2p, and then 3s and 3p. Okay, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Okay, so 4s, 3d, 4p. And then on the fifth line, it's 5s, 4d, 5p. And then on the sixth row, it's 6s. Okay, so that's the order that they go in. Now, I don't want you to memorize that. I want you to learn that this is the S, this is the P, and this is the D. And then you just start like you're reading a book. 1S, 2S, 2P, 3S, 3P, 4S, 3D. So you see how it goes? You don't have to memorize anything. You just have to learn. You start here at the upper left, and you just go line by line. Okay? Now, the s orbital can only hold 2 electrons, the p can hold 6, the d can hold 10. So now, when you're putting electrons, when you're doing electron configuration for an element, we're going to start adding in superscripts up here. So exponents to these S, P, and D letters. Okay, so for example, let's do sodium. The electron configuration for sodium, we're going to start out with 1s. So it has 11 electrons, so it's right here, okay? But we're going to start off with 1s, and then we have to go through that entire block, and that block has 2 electrons, so we're going to put a 2 there. Okay, there's nothing else on the first line. So now we're going to go 2s, and we have to go through 2 blocks here. Okay, we're making our way to sodium, which is number 11. So we have to go through these two blocks here. So it's 2s2. Then we're going to get to the 2p orbital. Okay, so 2p, we have to go through all 6 of these. Okay, so we're going to put a 2p6 there. And then we finally get to the third orbital where sodium is. It's in the first block, it's an S block, and it's the first one in that block, so we just put a 1. Okay? Now, one thing about this is if you add up these numbers here, it's going to equal 11, which sodium is number 11 on the periodic table. It has 11 electrons. So if you add these up, you do see that that is 11. So those are the 11 electrons in an electron configuration for sodium. So if you're asked to write the electron configuration for sodium, it's going to be 1s2, 2s2, 2p6, 3s1. Okay? Easy peasy. Now, let's do phosphorus. All right, so phosphorus is right here. It's number 15. So we're going to have to start the upper left, 1s. We have to go through both of these. So it's 1s2, nothing else on the one line. So go down to 2. So now it's 2s. We have to go through both of these. So it's going to be 2. And then the next thing we hit is going to be 2p. Okay, we have to go through all 6 of those. So it's going to be 2p6. Then the next line we get down is 3. So we're going to write a 3. This first block we have to go through is an S. So we're going to put an S. We have to go through both of those. So there's 2 there, so we put a 2. Then we get to 3p. Okay, so this is on the third line. This is the P block. Phosphorus is the 1, 2, third one over. So we're going to put a 3 there. Okay, so the electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3. Because we see phosphorus lives in the third block. Okay, and this is the third energy level. It's the p block, it's the p orbital, and it's the third one over, so it's 3p3. So really, all you have to do is look at this one to see where the element is, but you have to do the whole thing to get the arrangement of the electrons in those orbitals, in these s and p orbitals. Okay, so again, if we were to add up these exponents, we're going to get 2 and 2 is 4, 6 is 10, 12, 15, and phosphorus is atomic number 15. Okay, so that's how you can check yourself to see if you've done it right. All right, calcium is number 20, so it's right here. So we have 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so we've gone all the way through all of these. Okay. All right, so calcium is number 20, so it lives on the 4th row. So it's 4, and it's in the S block, and it's the second one over, 4s2. It's number 20 on the periodic table. So if we add up 2, 6 is 10, then 2 is 12, and 6 is 18, and 2 more is 20. We see those numbers add up to 20. Okay? All right. So for this last one, cesium, it's 55 right here. So pause the video and see if you can get the proper electron configuration. This is going to be the hardest one that you're going to have to do. Okay, so looking at cesium, we have 1s2, that's an S, 2s2, 2p6, 3s2, 3p6, 4s2. Now remember, this goes down to 3d10, 3d10 right here. That's a D. And then it pops back up to 4p6, 5s2, 4d10, it drops back down to 4d10, okay, 5p6, and then we get down to where cesium is, 6s1, 6s1, that's cesium, okay? So if you got that, very good. We'll continue to work on that. All right, and here is some elements on the periodic table. It's starting with sodium, which is 3s1. You can see here on this third level, 3s1, And then magnesium is going to keep the same electron configuration. It's just one more over, so it's going to be 3s2. And then aluminum, it's going to keep the same thing. Now it's 3p1, and then 3p2, 3p3, 3p4, 3p5, 3p6, etc. Okay? All right, so there is a shorthand for noble gas configurations because this is cesium. Remember how long cesium was? That's a lot to write. So shorthand, what shorthand does, it's also called the noble gas configuration, and it's also called core configuration. What they do is, in order to get this into shorthand, they look at the last noble gas that was passed through to get to this element. Okay, so let's go back. So cesium, okay, in order to get to cesium, it's right here. The last noble gas, oh, by the way, this group right here, this last one on the end, these are called the noble gases. So the last noble gas that we passed through before we got to cesium was xenon. Okay, and xenon is the fifth energy level, P6. Okay, 5p6. So what we're going to do is we're going to put a bracket. See, after 5p6, that square bracket, we're going to bracket this part off. We're going to replace that with the noble gas that represents, which is xenon, Xe. So we put Xe in the bracket just like that, and then we tack on whatever is left. So for cesium, it's easy. It's just 6s1. So this is the shorthand configuration for cesium. Okay, so it saves you a lot of time. So basically what it says is you're going to use the same configuration that xenon has, but then you're going to add a 6s1 onto it. Okay, so if you're trying to do an electron configuration for a noble gas, okay, so say we're trying to do one for xenon, what you're going to do is go to the noble gas that's before xenon. So here we would do krypton in brackets and then add on the rest of the configuration. So krypton is in 4p6, so we would go 5s2, okay, 4d10, 5p6. So this would be xenon's configuration. So you go to the gas before it and then add on the rest of the configuration. Okay, that's for shorthand. All right, now finally to diagramming. This is kind of like the Hog Hilton. And when you're diagramming electrons, these diagrams will already be drawn for you. And you had to remember those three rules. Okay, we're going to start at the lowest energy level, which it already is drawn for you. So it already starts you here at the lowest energy level. Okay, you can only add 2 electrons per box, and you have to add an electron in a single electron in an orbital before you go back and add the second one. Okay, and then when you add the second one, it has to be in the opposite direction. Okay, so say for example, we're going to do sodium again, which is number 11. So we would go 1, 2, 3, 4, and then when you get to P, see how these are connected? 5, 6, 7, and then go back and put a second one, 8, 9, 10, just like we did the pigs, and then 11 here. Okay, so where that really gets important is when you're diagramming something that stops in the p orbital, like oxygen. So if I were to look at oxygen, oxygen is atomic number 8, so that means it has 8 electrons. So we would go 1, 2, 3, 4. Now we're in the p orbital, so 5, 6, 7, and then 8. Okay, so this is the correct one. But if you did not follow those rules, then what you would do is mistakenly, you would have this, oops, I just erased it. You would have like this, 2, 4, 6, 8, and that would be wrong, okay? Because this one's empty, okay? We had to have an electron there before we put a second one in there, All right, so it's just like the Hog Hilton. And the other way of diagramming is like this that you'll see. And in this type of diagramming, we're adding in x's. So here it would go 1, 2, and this direction would mean one direction of spin. This direction would be the second direction of spin. 3, 4, 5, 6, 7. Oops, I did it. Okay, so don't make that mistake. Okay, so let's start over. Don't make the same mistake I did, or you're going to end up getting these wrong on a quiz or a test. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's for sodium. Now, if we were doing oxygen, which has 8, we'd go 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, so that's how you do diagramming. All right, and so that's it for this video. Make sure you slap that like button right across the face, and make sure you give me a subscription and a thumbs up.